Hi everyone, today we will cover cluster architecture for CKA Domain 2 troubleshooting. I'll guide you through the cluster anatomy, the processes that run in it, and exactly where to look when things go wrong. Let's dive in. This video is aimed at CKA candidates. If you are studying for the exam, treat this as a focused troubleshooting checklist. Understand what each component does, how they talk to each other, and the practical commands and check to run when something breaks. In Domain 2, we focus on 4 areas: the cluster and its nodes, the core cluster components, monitoring and resources check, and services and networking. I'll walk you through each area in sequence so you know both the theory and the troubleshooting steps. At the highest level, a Kubernetes cluster is a group of machines working together, a control plane that makes decisions, and worker nodes that runs your workloads. If you are looking at the diagram on the slide, imagine the control plane at the top and worker nodes below it. The control plane holds components that accepts requests and record state. Worker nodes run pods and actually execute the containers. Troubleshooting starts by asking, is the problem with the decision making, which is the control plane, or the execution, which is the worker node? Now first, the node agent, which is the kubelet. It runs on every node. It continuously reports node status to the control plane. Its core job is managing container on its node, pulling images, starting and stopping container via the container runtime, and enforcing the pod specs the API server provides. When the API server gives an instruction like create, update, or delete a pod, Kubelet implements it. Kubelet also collects resource usage on the node and invokes network and storage plugins so pods gets their networking and volumes. If you need to probe the kubelet, check its pods and exposed endpoints for metrics and pod information. These are the places to look when pods fail to start or nodes report weird conditions. Now coming towards the demo. In this demo, we will disable the unauthorized and unauthenticated access via kubelet. Now first checking the services of the kubelet. Here you can see the configuration file location. Now accessing this file. As you can see that anonymous authentication is enabled. And the read-only port is also available. Now first checking the normal operation. If I give the ports command through direct link or a direct request, we can see all the pod information because the request is not authenticated. Now first changing the anonymous authentication, changing it to true, changing the true to false, and then authorization we change it to webhook. And for read-only ports, we don't want that anyone access the metrics as well, so we configure 0 as the read-only port. Now restarting the kubelet. As you can see, now we are not able to access the pods through direct request, and we are not able to see the metrics as well. So in this form, you can enable the kubelet security, or you can check for any misconfiguration in the kubelet configuration file that is obtained through checking the services of the kubelet. Now moving forward, Kubelet talks to the container runtime through a standard interface called the CRI. This makes Kubelet runtime agnostic. Because of the CRI, which is Container Runtime Interface, Kubernetes works with Container D, CRIO, or other runtime without changing the core logic. Container D is a common lightweight runtime you'll see in modern clusters. For troubleshooting, containers directly use the runtime aware CLI, for example, CRI-CTL, or normally we call it CRI-CTL, to list the containers, inspect them, check the logs, and execute the into the running containers. This helps you separate container level problems from the Kubernetes level problem. In the next demo, we will be using the CRI-CTL command to check the logs and check the status of the different containers that are running on the control plane. Now moving forward, Kube-Proxy runs on each node and implements the networking rules that let the services reach the correct pods. Now think of it as the traffic director. When a service is created, Kube-Proxy sets up the local networking rules to forward traffic to the correct pod endpoints. In many clusters, Kube-Proxy runs as a pod in the control plane namespace and is deployed as a daemon set, so every node has one, and when you delete it, it will automatically be created. If client can't reach a service, check the Kube-Proxy logs and the local forwarding rules on the node. That's often where a service's reachability problem shows up. Now moving forward, we come towards the Kube-API server. The API server is the cluster's front door. Everything like kubectl commands, controller, kubelets talk to it. It authenticates, authorizes, validates, requests, run admission controllers, and persist cluster state to the cluster store. When you create an object, the API server is responsible for receiving that request, first validating it, and then storing the status changes if any are requested. If the cluster is unresponsive or kubectl calls fails, the API server is the first point to check. Now for quick troubleshooting, what happens is like the client request arrives at the API server. The API server first validates, authenticates, and persists the object. Other components like scheduler, controller watch for the changes and react accordingly. If something stops at any step, the API server logs and the static manifest on the control plane nodes are your first checkpoint. Now coming towards a live demo. In this live demo, we will be troubleshooting the Kube-API. As you can see, when I run the kubectl command, it is unresponsive, and the error shows that 6443 was refused. So 6443 is the port for the Kube-API. Now checking the CRI-CTL first and checking the container. There is no container being built. Now checking the log files. There is no log file created as well. So actually the container has not run for once as well. Now checking the logs. Now moving towards the configuration file. The manifest for the Kube-API. Now you see that the metadata, there is a semicolon used instead of a colon. Now if we change it, this is the one error. Now let's see if we can run the kubectl command again. Let's first check the container. Now the container has been built. The container is available. Now we can check the logs of this container. Now if you see the logs, again checking the container, giving the proper container ID. Now you can see that there is an unknown flag, and instead of modus has been written. Now we can check from the configuration file and make the correction accordingly. Now again checking if the container is now available, the Kube-API container through CRI-CTL command. Now checking the logs again. Now if you see that there is a connection refusal and a port number 23000 has been used. Now checking the 23,000 port. Now you can see that the etcd is configured with 23,000 port, but the actual port number is 2379. Now after making the changes, let's see if the Kube-API server is now responding and we are able to run the kubectl command again. Yes, now it is working. So there were 3 misconfiguration, and we were able to find those misconfiguration through the different kinds of logs that are available. Now moving forward, the controller manager runs controllers that ensures the cluster's actual state matches with the desired state. Things like replica sets, jobs, endpoints, persistent volume, service accounts, and more. Controller continuously compare current state to the desired state and make the changes to converge that state. For example, restarting pods when replicas drop. Controllers don't receive external requests directly. They act through API server. If the resources aren't reconciling as expected, the control manager logs and it watches the cycle, and its watch cycle are where to investigate. Now coming towards the live demo. Now as we can see that all these control components are present in the Kube system namespace, and here the controller is not working. Now checking the logs of the particular pod. In the logs we can see that there's an unknown flag, that is sidecar insertion. Now let us open the configuration file of Kube controller and find the flag that is causing the error. Now removing the line which is not which is causing the problem, and then again seeing whether the pod is not available is now available or not. As you can see, now the pod is running. Now moving forward, etc is the cluster's persistent store, the single source of truth. It stores all the objects and configuration like pods, nodes, secrets, roles, everything. Any change you make is first written to etcd. Other components read or watch etcd for updates. If etcd becomes unhealthy, the control plane loses its memory that can break the scheduling, reconciliation, and more. For diagnosis, confirm cluster membership, health, and that writes are succeeding. Now moving forward, the Kube scheduler. The scheduler is responsible for choosing the best node for each pod. It filters out nodes that don't meet requirement, then ranks the remaining nodes and picks the best match based on the scoring rules. It watches the API server for unscheduled pods, then assign them. If pods are stuck in the pending state, scheduler condition and logs are the right place to look for. Check why pods failed filters or why the ranking picked a node that later rejected the pod. So if the pod is not scheduling, you the control panel you want to check is the Kube scheduler. Now let us wrap it up. During troubleshooting, determine whether issue exists at control plane or the node level. The first step is to determine where to look for, the control plane or the node level. Now the control plane has multiple control components. Then we have to follow the component specific to each problem. See their configuration file, know the configuration file location and the specific ports, and try to interpret the logs collected from different sources. If this helped, like and subscribe the channel, and good luck for